Yes, Varun. Good evening. Okay. Today we are going to see the remaining part of the lesson, okay, which is much more interesting than the previous one. Okay. Yeah. Before that, just one more question which we have not discussed in the last class. Of course, this is also based on the Fleming's left-hand rule. Okay. So many questions of this type will be there are more possible for appearing in the board exam. Let us see this question. A positively charged particle, say positively charged means it cannot be electron, so alpha particle, which is projected west, is deflected towards north by a magnetic field. Find the direction of magnetic field. So whenever there is a concept regarding this magnetic field and then the direction of a particle, okay, so simply we have to assume that left hand rule. Okay, so what you have to do, first you have to stretch the first three fingers of your left hand mutually perpendicular to each other. Now the point is that the particle is projected towards west direction. Okay, so if you keep the three fingers mutually perpendicular to each other, which finger points the direction of movement of the direction of current? Which finger? The middle finger. So you have to keep your this middle finger which is in the direction of the particle. Okay, so in which way we can keep that? If only you point it towards yourself. Okay, because when you say that it is west, the usual method of finding the direction is that when you are facing east, your back will be the west. So you have to keep your finger in such a way that the middle finger is pointing yourself, that is west direction. Okay, so if it is pointing towards yourself, okay, to your left will be to your left. How will you find out? Come on, keep your finger like this. Keep your middle finger pointing yourself. Okay, middle finger pointing yourself. Okay, and then to your left side, that is thumb point the direction of force. To your left side, you can see that to your left side. Okay, if you point towards yourself like this, just look at that. The vadivel kepaaliya தேவையா உனக்கு அப்படின்ற மாதிரி. Okay, just imagine like this. Okay, so middle finger is pointing towards yourself. On the left, that is thumb. To your left, thumb is there. It is showing the force. Okay, what is the direction of magnetic field? Upward. But what I have given here? Upward. So this is the answer is only simple. But what is the thing that you have to keep the finger properly? Okay, right? So east to your front side east, back side west. So this way you have to keep and then find out the direction of magnetic field. Okay, similar question will be in a different way that we'll answer at the end of this session. Okay, let us go to the next one now. The next concept is electric motor. You know that what is electric motor? It is based on the principle of Fleming's left-hand rule. Okay, so when a current carrying conductor is placed in magnetic field, it experiences a force. That is the same principle which is utilized in all the motors. Because there may be a question, state the principle of electric motor. So what will you say? Simply we can say that electric motor is based on the principle of Fleming's left-hand rule. That is, it's a rotating device. You know that when you switch on that, which is something like a fan, okay, or a CPU fan, everything, all the motors which we are using, they are all nothing but, even the grinder which we are using here, mixie, everything is nothing but electric motor. So it's a rotating device which is converting the electric energy into mechanical energy. So what the current we supply, that is utilized to create the force. So that the force is making that mechanical energy. It is resulting in mechanical energy, that is movement. So this is the point you have to remember. In a motor, which energy is converted to what form? electrical energy is converted into mechanical energy. Now we are going to see in detail, okay, the functioning of electric motor, how to construct and how is it working. And these are the components, that is the different appliances or component in electrical fans, refrigerator, mixers, washing machine, computers, even the MP3 player, which we call it a CD player. All these appliances are nothing but working with the help of a electric motor. So there may be a question, give examples of devices that run on electric motor. So you can just cite an example like this. Okay, just look at the pictures and remember. And one more thing, keep your volume at the desirable level, because you are using headphone, you know, it may create headache. If it is too loud, it may be undesirable. So keep it at a desirable level, optimum level. Okay, right. Now let us go to the electric motor, the construction and working of an electric motor, which is very same principle which you have learnt when we were investigating the motion of a conductor in a magnetic field by using a aluminum rod. We did, isn't it? The same thing only, or you can say a conductor placed in a magnetic field will experience a force. Same thing only, but little bit in detail. Right? Here, in all the electric motors, the coil will be in a rectangular form. Right? The reason for this is, at the end of this point, that is this session, you will understand why should be in a rectangular form. Why should not be a rod like, or why should not be like a circular form? Why it should be in a rectangular form? Right? For this question, you have to answer me at the end of this chapter. Okay? Right. Now it is consisting of a rectangular coil, which we name it as A, B, C, D. Right? Before going deep into this topic, you just keep that Fleming's left hand rule in your mind, always ready. So we are going to apply that here. Now this coil is placed between the two poles of a magnetic field. How the magnetic field is created? Powerful magnets, north and south pole. So that in between that, magnetic field will be created. Okay, the magnetic lines of poles will start from north and here, from here to here, it will be uniform. Now this coil, which is rectangular in shape, hereafter we can call this rectangular shape coil as armature. It is otherwise called a armature. Right? It is kept in the magnetic field such that this two arms, we call these two as arms, AB and CD. These are the two arms of the coil. Right? And these two arms, AB and CD, are perpendicular to the direction of the magnetic field. You see that? This is perpendicular to the direction of the magnetic field. Right? Why should be in perpendicular direction? This is the last point which we studied in the last session. Why should be the coil placed at an angle 90 degree to the direction of magnetic field? Can it not be kept at 45 degree or 30 degree? Why should be perpendicular? No. I'll put the question like this. When will a conductor carrying current will experience maximum force? Yeah? Tell me. That's all. That is why the coil is placed so that it at a 90 degree, so that it will experience the maximum force. Okay? Right. Now, usually when the coil is in a rectangular form, it will have two ends. You know that. The two ends of the coil, they are connected to two halves of a split ring. You know the split is nothing but cutting into two, split it into two. A circular ring is there, it is cut into two halves. So one half is called P, the other half is called Q. So the two ends of this coil, they are connected to this split ring. Remember that this is going to get confused when you are going to study the generator. In generator also we are going to use rings, but they are called as slip rings. Slip, and it is split here. Split means cut two halves. Okay, straight away. A circle is cut into two. So remember that alone. So the two ends of this rectangular coil are connected to two split rings P and Q. Right? And this inner side of these halves, they are insulated attached to an axle. Insulator means they are not connected to the shaft. We call it as shaft. Okay? It is a rotating rod, we can say, axle we can say. Okay? And they are insulated so that no current will pass through that. That is why it is kept insulated. Right? Now, the external conducting edges of this P and Q, the split rings are there, no? P and Q. They are attached to two carbon brushes, stationary carbon brushes. The carbon brushes is nothing but it is for conducting the current to the external circuit. Okay? Or to pass the current through that, they are connected to two brushes, X and Y. We name this as X and Y. So respectively means this Q is connected to, P is connected to X and Q is connected to Y. So this is the connection. Okay? Now let us see how this is going to work. Okay? This is the construction. So far what you have seen is construction. Very simple one. The coil is in the form of rectangle. It is placed between the powerful, perpendicular to the powerful magnetic field. Okay? And the two ends of the coil are connected to the two split rings, P and Q. The two rings are connected to the carbon brushes X and Y. This is the construction. Now, as soon as you plug the key, what will happen? The current will start flowing. So, what is the direction of current? It will start flowing from this direction. Okay? This is the direction of current. It enters the coil ABCD from the source battery through the conducting brushes. I said carbon brushes, X and Y. Here, when the current is switched on, it will start flowing through this X carbon brush. So from here it will go. Here you can see the current will enter through this AB, and after flowing here, it will come down. That means the direction of current will be reversed. You have to remember. That is why the shape of the coil is kept in a rectangular form. You have to remember. Okay, so it will start flowing from X, enters AB, again it will start flowing through C and D and leaves the circuit through the Y brush. Okay, so in the arm AB, the current is in one direction, arm CD, the current is in the opposite direction. Okay, right. Now, once the current is start flowing, we are going to apply the Fleming's left hand rule. Now apply that. What is the direction of current? Keep the finger and apply that. This is the direction of current. Okay. Keep the finger and see. Keep your left hand in such a way that your middle finger is showing the direction of current. Okay. So this is the direction of magnetic field. Now keep that and apply that. What way it will be showing the direction? Come on. See that? I'll show you how to keep that. You have to keep that towards the book. Okay, so this is the direction of current. Okay, and then this is the direction of magnetic field. You see that? I'm going to keep like this. So that opposite side. That is, your hand should be bent towards the board or notebook. So that you can see that this is the direction of magnetic field and this is the direction of current which is flowing towards the board or inward. Now you can see the thumb is downward. Isn't it? Yes or no? So what will happen? A force will act on this AB which is pushing downward. Are you able to get that point? Yes? If you keep like this you can see. So that the arm AB will be pushed down and arm CD will come down. Like this. You can keep the book like this and check that. So that it will rotate like this. Okay? From here it will rotate like this. Understand? Right? Now, since the coil is attached to a axle, so the axle is free to rotate. Right? So, when it is moving downward, what is the direction of this? whether it is clockwise or anti-clockwise. When it is rotating this way, what is that called? It is anti-clockwise, right? Arm AB will go down, arm CD will move upward. That means it is anti-clockwise direction. So the axis which is attached here also will rotate along with that. Now, after half rotation, what happens? Because we have got a split ring in the form of semicircle. So until the semicircle is completed, the coil will keep on moving. Once the circuit is, that is the half of this is crossed, what will happen? The second of this will get into connect with this. That is the arm, that is the carbon brush Y will be coming in contact with that. Okay. So Q will make, after half rotation, Q makes contact with the brush X and P with Y. That is, they will change that. The carbon brushes are stationary, but the split rings are moving. So once they rotate, what will happen? Earlier P with X and Q with Y. Now P with Y and Q with X. That is half rotation. Now what will happen? The current will start flowing in the other direction, reversing the current. So what will happen? Instead of current flowing from ABCD, now the current will flow from DCBA. This kind of changing the direction of current, right? Yeah, DCBA. And this kind of device which we use here is as split rings. No? Earlier in the previous session I showed that commutator, no? DP/dt switch I said, for throwing the current in the opposite direction. Here also, since we are using that for changing the current, we can call these two split rings are used as commutator. They are used as commutator. So what is a commutator? A commutator is a device that will reverse the current, reverse the direction of the current. This is another question you have to remember. What is the use of split rings in the electric motor? What do you have to say? The split rings are used as commutator. A commutator is a device that is used for changing the direction of the current. That is the answer you have to give. You have to give in 2 lines. One is, what is the purpose of split rings? That is, they are used as a commutator. Then you have to say, what is a commutator? It is a device that reverses the direction of current. So that is the role of the split rings here. Okay. Now, after reversing, what will happen? The reverse of current also reverses the direction of force. Already we saw that the force was going downward. That is, the arm AB is going downward, isn't it? Arm CD was moving upward. Again, when it is reversed, what will happen? The arm AB will move upward and this will go downward. Again, the AB will be earlier pushed down, now it will be pushed up, because now we can remember that in the beginning it was like this. That is, it was like this in the beginning. Say this is AB and this is CD. Okay? In the beginning it moved like this. Okay? 1/2. That is, this is 1/2. Now, earlier it was AB, this is CD. Now this is CD, this is AB. Earlier AB was moving downward, now the AB will be moving upward like this, 1/2. Again 1/2 downward, upward, like this it will keep on rotating. Okay, is that clear now? Do you have any difficulty in understanding this? Yeah? I'll repeat again, see that? Say this is AB and this is CD, this side is CD. Okay, AB, the direction of current is this direction. Here the direction is in this direction. Now once the current flows, this will go down like this. 1/2 of the split ring completes the circuit. Now what happens? This is AB and this is CD now. But in the AB earlier it was direction of current is inward, but here it is outward. The same AB has come here, but the current is in the opposite direction. So instead of going downward, what will happen? It will go upward. So 1/2, again another half complete. Like this, it will keep on rotating because of the change in the direction of the current. Okay. So the armature or the rectangular coil will keep on rotating until such time when the current stops. So if the current is keep on flowing through the circuit, the coil will also keep on rotating in the anti-clockwise direction. So this will go down, this will go up, again this will go down like this, it will keep on rotating. So once this axis is connected to the, let's say for example if it is used in a fan, this axle will be connected to a fan, leaves. So that when it is rotating, the leaves will also rotate. Or if it is connected to a sewing machine by using a belt. So once it is rotating, the wheel will also rotate like this. By using this axis, by using this rotational effect, you can keep on running any machine. Okay. So for every half rotation, it is changing the current. Is that clear? Right. Now, when you are talking about commercial motors, right? So the commercial motors should be more powerful, isn't it? So to have this more amount of force acting, we have to use a permanent magnet. In place of electromagnet, the commercial motors will use permanent magnet. And they will have a large number of turns. So that if more number of turns are there, the magnetic field will also be more, so that the force will also be more. And a soft iron core on which the coil is wound. So these are the three important points you have to remember regarding the commercial motors. Yeah. Yes? Yes? Electromagnet will be more powerful than the permanent magnet. You remember that. The ordinary magnet is called the permanent magnet. The bar magnet or everything, you know, the magnetic metal. The magnet is ordinary magnet. They are permanent magnet. They are somewhat weaker. When you are using electromagnet, it will have more power. That is why the commercial motors will have electromagnet. How to create electromagnet, you know that. Have you ever opened a fan? Have you ever seen a fan inside a fan? Ceiling fan or a table fan? No. If possible, see that. You've got a lot of fans in your house, you know, you can take one and remove that and see. Doesn't matter, no, we learn only by experience. Here, I have shown here, there is a rectangular coil. This is called armature. Okay, this is called a armature. And we have got so many coils, you can see that. Each rectangular coil has got number of turns. Like that, many coils are there, so that for producing this effect. But where is the magnetic field? This armature will be kept inside a circular box, circular iron core. That iron core will also have so many coils. And when current is flowing through that coil will become a magnet. That is called electromagnet. So inside that electromagnet only, this armature will be kept, so that it will have the experience the force. Okay, that is what they say. Instead of permanent magnet, they will use a electromagnet. Okay, and you can see that large number of turns are used to produce more amount of force. And this is called a soft iron core. You can see that where it is kept wound inside a soft iron core. All these are the factors which will increase the power of the motor. Right? So that is what I said. This is called armature. You have to remember, rectangular coil with so many turns, which is nothing but called a armature. And this is only to, all these points are only to enhance the power of the motor. There may be a question, how can the power of a motor, DC motor, be increased? So what you have to say? You have to remember these points. One, using a electromagnet instead of permanent magnet, by having large number of turns of conductor, coil, and by using a soft iron core on which the coil is wound. These 3 points you have to remember to increase the power of a DC motor. Right. Now this is the simplest electric motor, which you can see a video how to build the simplest electric motor. Okay, by using the Fleming's left hand rule. Just watch that. It will be very interesting, so that you can also make at home. Just a minute. Look at that. It's the simplest method to make a magnet. You know that this is the copper wire where there will be a coating, insulating coating will be there. To make a contact, we have to remove this coating so that the current will flow through that. That is for making the contact. Look at that. And it is instead of a rectangular coil, here we are using a circular coil, so that it's only for experimental purpose. It need not be. It can be rectangular also, but here it is very easy to wound. That is why we are making this as a circular coil. I didn't say that we cannot use circular. To the commercial motors, which will have to have more power, they should have this rectangular. That is for continuous rotation. But also there we are using two magnets, north pole and south pole. Here we are going to use only one magnet, which is called a unipolar, monopolar we can say, or unipolar motor. By using only one magnet, because though you are using one magnet, it will have both the poles, north and south pole, right? But the magnet is not going to be placed between the poles, but here nearby that, in the magnetic field. This is the actual application of Fleming's left hand rule. Now the magnetic field is here. It is when the coil is placed in the magnetic field where the current is flowing through the coil, it is going to experience the force. You can see that. Now see that once it is connected, it will start rotating. Very simplest one. They have used bell pins here, that is gem clip here, and the coil is connected in a form of circular, and the magnet is kept here so that the magnetic field will be created here around the magnet. You know that within that vicinity only it can work, it will function. So this is how it is keep on rotating. Here there is no split rings, there is no carbon brushes, but here this is used as a carbon brush, and the split ring is not there because since we are using only one magnet, it is called a unipolar, and it will keep on rotating. Once the magnetic field is cut, it will stop because it cannot experience the force. Okay. So this is one of the simplest motor which you can also try at home. And remember that we are going to see about a greatest scientist whose academic background is zero. He has not gone to the school, but he is named one of the greatest scientists in the science world. How is it possible? Because he was very curious about knowing things. He kept on doing some experiments by just, exactly. You would have studied about him in the textbooks. So that is the wise way of learning things. So since you are given ample time, when you are studying 10th standard, you don't have much work to do. So these kind of simple experiments you should try at home, then only you can develop your application knowledge, how to apply this concept in your day-to-day life. That is possible only when you get time and apply that. You can try that. Now let us go to the next point. This is what I said in the earlier one. The question will be like this: what is the principle of an electric motor? Okay, this is the book bag question. You know that electric motor works on the principle of magnetic effect of electric current. That is based on Fleming's left hand rule. That is, it is based on the fact that, it is based on the fact that when a rectangular coil is placed in the magnetic field and current is passed through that, it experiences a force due to which it rotates continuously. Okay, electric energy is converted to mechanical energy. These are the 3 points you can write on the principle of electric motor. Okay. And here there is no hardened rule that we have to write the same sentence. If you understand the concept, you can just relate that, right? At least if you give 3 points, you can correlate with each one. Simply we can say, what is the principle of electric motor? We can say the electric motor is based on the principle of Fleming's left hand rule. This is quite sufficient. But they may ask you whether you know that Fleming's left hand rule. So that an extension of the previous one. When a rectangular coil is placed in the magnetic field, when a current is, or we can simply say, when a current carrying rectangular coil is placed in the magnetic field, a force is acting on the coil which makes it rotate continuously. This way you can put it in any different way without changing the meaning. Am I clear? Right. The other question which I said earlier, what is the role of the split ring in the electric motor? In an electric motor, a split ring acts as a commutator. This is the answer. That's all. If you are thorough with this word, commutator, spelling is correct, then you will be given mark. The only thing is that you have to know, you have to explain your teacher or examiner that you know much more about this commutator. That is for changing the direction of flow of current. A device that reverses the direction of flow of current through a circuit is called a commutator. Okay, you are exposing your knowledge to some more extent. That is how we have to give the answer. Right. If it is a 1 mark, this is enough. Split ring acts as a commutator. That is enough for reversing the current, direction of current. The next one which we have been discussing about, the great scientist Michael Faraday. Okay. So the topic is electromagnetic induction. Do you know what is meant by induction? Yeah? I am not asking you scientifically. Do you know the literal meaning of English meaning? What is meant by induction? Don't go deep into the science. Induction. What is meant by induction? Yeah? Not sure about it? Don't know. No, very good. Now we are learning, and sitting in front of a laptop or a desktop, you are learning something. If your mother is preparing some delicious sweet item, okay, just imagine. The fragrance coming from the kitchen and reaches you. What will happen to your mouth? It will start producing saliva, isn't it? This is nothing but induction. Tempting without any touch. You have not taken the sweet, you have not put into your mouth, it is not having any physical contact, you are not eating that, so that you feel happy or the saliva will start. But without that contact, you are able to produce saliva in your mouth. So this kind of action is called a induction. Right? Here we are going to produce current without having any physical contact with the two objects. Let us see how. And this was actually discovered by the great scientist Michael Faraday in the year 1831. And he said that this is actually the reverse effect of the magnetic effect of electric. Earlier we said that when a current carrying conductor is placed in the magnetic field, it experiences force. Now we are reversing that. When a coil is placed in the magnetic field, when it is rotated, definitely what it should produce? It should produce current. This is the reverse effect of the magnetic effect of electric current. That means whenever there is a magnetic flux linked with the coil changes. What is meant by magnetic flux? You have not learned about that, isn't it? It's a new concept. Do you know what is magnetic flux means? Have you heard about this word magnetic flux? Yeah, new concept, very good. It is nothing but the number of magnetic lines of force crossing per unit area. Crossing per unit area. That is called the magnetic flux. Okay? It is actually indicated by a letter. You will study this in 12th standard. It is indicated by letter phi. Phi. Magnetic flux. Number of. Yeah, there are different ways to calculate that. That is what I said. It is the extended portion of your lesson. At present, you know that it is nothing but magnetic flux is nothing but the number of magnetic lines of force crossing per unit area. Of course, this is also not going to be asked in the exam, of course. Because the word is there, you have to understand what is flux means. Magnetic flux means number of magnetic lines of force crossing per unit area. Now this number, after all, we say simply when the magnetic field is changing. Instead of saying that magnetic flux, yeah, we'll say simply when the magnetic field is changing, right? What will happen? This change in the magnetic field will produce current. Okay, EMF will produce, and the EMF will be producing a current. This is what was observed by this scientist, right? Okay. Now we call this as a relative motion. That is, he showed that this EMF, we call it as EMF. You know what is EMF? You know what is EMF? Arun? Yeah. Electromotive force. And this EMF is generated whenever there is a relative motion between the conductor and the magnetic field. Yeah. We call this as relative. What is meant by relative? We say relative motion. That means with respect to the other one. Right? With respect to the other one. We say, for example, yeah, I'll tell you. For example, what is the distance of moon? If somebody asks, what will you say? Say, for example, you will say the exact value, say 1,78,000 kilometers. The next question will be, from where? Is it from the moon? No. Is it from the moon? Is it from the Pluto? Or is it from the earth? Because we are on the earth, they can say the distance of the moon only relative to our earth, right? Relative to our earth. From earth only we can say. So by fixing that earth as the point, origin, we are measuring the distance of the moon. This is called relative. Okay? With respect to moon, with respect to earth, the moon is revolving around the earth. It is called relative motion. With respect to sun, both moon and earth are revolving around the sun. These are all called relative. Here we are talking about two things, a conductor and a magnetic field. Now there are two possibilities. That is, the conductor can change, that is, the conductor can move, or the magnetic field can change. This is called relative. When the conductor is changing, when the magnetic field is changing, the conductor is not moving. When the conductor is moving, the magnetic field is not changing. We call this as relative motion. Right? Have you got it? Yeah. Now, in this way, if the EMF is produced, it is called induced EMF because it is not in contact with each other. Okay, that is why we call it as induced EMF. And this phenomenon of producing an induced EMF due to the relative motion between the conductor and the magnetic field is called the electromagnetic induction. Okay, definition. So if somebody says, what is electromagnetic induction? What is electromagnetic induction? The phenomenon of producing an induced EMF whenever there is a relative motion between the conductor and the magnetic field. That's all. Very simple words you can put. The phenomenon of producing an induced EMF whenever there is a due to the relative motion between the conductor and the magnetic field. That is called a electromagnetic induction. Okay? Right. That's all. Right? And this induced EMF, you know that this force with which the electrons are moving. Due to this force, the energy with which the electrons are driven, they will create a flow of current. They will constitute a flow of current. Such current is called a induced current. Right? Due to this invention, he made a breakthrough in discovering how a magnet can be used to generate electric currents. If this was not found, we may not have generator nowadays. For example, if you take a power plant, hydel power plant, where the motion of the water is converted into electricity, the mechanical energy of the water, it is used to move the fans, such a big turbine we say, turbine. When the fan moves, the coil attached to that will start moving, so that will produce electricity. So these things may not be possible if this breakthrough was not there. Such a great discovery, invention we can say. Right. Now, we know that when a current carrying conductor is placed in the magnetic field, it experiences a force. This causes the conductor to move. Right. Now, we are going to have the different situation that a conductor is moving inside a magnet, the opposite of that previous one. Right. The conductor is moving inside a magnetic field. or a magnetic field is changing around a fixed conductor. This is was nothing but generator. In a generator, what is changed? The conductor is moving inside a magnetic field. Okay, or the magnetic field is changing inside where the conductor is located. This is what going to happen in a generator. Okay, let us see. Now, before going to that, there are two ways to understand the creation of this EMF, that is electromagnetic induction. Okay, so to understand that, we are going to have some experiment also. Here, a coil of wire. You know that it is like a solenoid. A coil of wire AB having a large number of turns is taken, and a star bar magnet is taken. We are going to investigate by using this bar magnet. By moving that to and fro method, to and fro direction, we can change the magnetic field. Okay, or we can keep the magnets at a stationary position. We can move the conductor like this so that the conductor is moving. These are the two methods, relative motion of a conductor and a magnetic field. Okay, so these are the ways. Now, let us observe this activity. What are going to have? The coil is wound on a cardboard like this. A conductor, we call this as conductor. It is connected to a sensitive galvanometer. What is the use of the galvanometer? You know that. Tell me what is the use of the galvanometer? Pardon? Exactly, very good, very good. To detect the flow of current. Exactly, what you have told is right. This is used for detecting the flow of current in a circuit. Okay, so the two ends of the coil. This coil is connected to a sensitive galvanometer. Now, look at this activity. There is a video which will help you to understand when a magnet is moved inside a coil, what is happening. Let us see. Look at that. It's very nice video. You can understand easily. Look at that. Now here you can see this is the coil which is having a long number of turns. Now the magnet is moved inside that. You can see we are using an ammeter. Of course, instead of galvanometer, we are using ammeter. Ammeter is used for measuring the current. Galvanometer will detect the current. Now you can see the direction. When the magnet is changed, you can see the direction. Earlier it was on the left hand side. Now it is on the right hand side. When it is moved faster, you can see how the deflection is. When it is moved slower, deflection is there. Now instead of analog meter, we are going to have digital meter. We call it as multimeter. And using this also we can detect the current. Now you can see a circular coil is kept. The magnet is, if magnet is not there, it is showing zero deflection. When it is moving only, it is showing some number. You can see that the north pole is now kept inside. See that there is no. Once it is at a rest position, no deflection. Only when there is a movement, you can see that it is showing some deflection. Now you can see there are two coils. One coil is moving on the other coil. You see, it is on the other one. Now, there is no contact. It is only sliding inside, but it is not in contact with that. Deflection is there, exactly. Now you can see two coils are there. One coil is on the other one. Right? Now, when the plug is inserted, when the plug is pressed, you can see that there is some deflection. That is, the current is starting from 0 to the maximum. Yes, whether it is south pole or north pole, the deflection will be same. But the only thing is, how fast you are moving, whether it is slow or fast. The faster you move, more deflection will also be more. If it is slower, deflection will also be lesser. That means, the production of EMF is basically based on the rate of movement of the magnet, or the rate of change of magnetic field, we can say. How fast the magnet is moved. Now, on seeing that, after performing, Faraday has listed the inferences. You can see there are some inferences. The question which he asked, you can see that now. The first one the first inference made by Faraday is, whenever there is a relative motion between the coil and the magnet, the galvanometer showed a deflection indicating the flow of current, indicating the flow of induced current. That means when the magnet is moved or when the coil is moved, this is called relative motion. So the galvanometer showed a deflection. That means it is indicating the induced current. My student will never yawn in front of me. Varun is yawning. It shows that you are becoming tired. How can you become tired in physics class, man? Yeah? Okay. Right. The second one, the deflection is momentary. You know, momentary is nothing but for a short while. How short it is? It is lasting so long there is a relative motion between the coil and the magnet. And you would have seen that in the previous video. When the magnet is at rest position, there is no deflection. Only when it is moving, the deflection was there. So the deflection is lasting only when there is a movement. That is the second point he made, second observation he made. The third observation is, you asked me, if you change the magnet, that is, if you are inserting and when you are taking out, these are the two directions in which the magnet is moved. So when you are inserting, if the deflection is one side, when you are withdrawing the magnet, the deflection is on the other side. That means the direction of current is also changing. So this is the third observation. The direction of the flow of current changes if the magnet is moved towards and withdrawn from it. Right? And the fourth one, the deflection is more when the magnet is moved faster. And the deflection is less when the magnet is moved slowly. So the rate of movement. And finally, after reversing, that is, when you are reversing the magnet, instead of north pole and south pole, you are reversing with the south pole and north pole pointing towards the coil. What is that observed? The same results are observed. Only thing is, the current is reversed. Current is flowing in the opposite direction. So, these are the 5 inferences which is made by Michael Faraday. So, these 5 points are very, very essential for you, because any point may be asked as a multiple choice or 2-mark question. Okay? So, they may give a situation. Imagine that the magnet is moved like this, pointing north pole towards the coil. What is the direction of the force? What is the direction of induced current? Like this they may ask. So you have to remember all the 5 inferences made by Michael Faraday. Now in the video, the last portion we have seen, isn't it? The last portion with the 2 coils, isn't it? That is what this diagram shows. This activity is in which the moving magnet is replaced by current carrying coil. In the last part of the video, we didn't have the magnet, isn't it? We had 2 coils. So one coil is producing the magnetic effect of electric current. When the current flows through that, this will produce magnetic field, and due to this magnetic field, this coil will induce EMF. This is what we say, without any contact with this, the change in this magnetic field will produce current in this coil. Now you can see that both the coils are detached, they are not attached, and the galvanometer is attached in the second coil only. And here we have got a battery and a plug key. Okay, using this, you are going to understand how this the concept of electromagnetic induction. Look at that. And these 2 coils have got a different number of turns. Say for example, here we have taken 50 and 100 turns. 50 and here 50 and here it is 100 turns. And they are inserted over them on the conducting cylindrical coil. As we have seen in the video, one coil is inserted over the other one. Now, we are going to connect the coil 1, which is having a large number of turns. You know why we are taking this large number of turns? So that it will produce enough magnetic field. That is why we are taking a coil with a large number of turns first. And it is connected with the series with the battery and a plug key. And with the second coil, another coil is connected with the galvanometer. Coil 2 is connected with the galvanometer. Now what is our aim? We are going to study the effect. Why series? Because the current has to flow through that, no? So that the current will start flowing through that. So otherwise it will not flow. That is why it is in series. Now, once you put the plug key, what will happen? The current will start flowing. Once the current starts flowing, will there be any deflection in the coil or not? Definitely. There will be some deflection in the galvanometer. That means once you plug the coil, instantly it will jump. The deflection, the needle in the galvanometer will jump. That shows that there is some induced current in the coil. But the interesting thing is that the change in this coil, the current is, how the current is changing? Once you plug the coil, the current is 0. At the time it is 0, and to make a steady current, it will take some few seconds. From 0 to the maximum, we say. From 0 to the maximum, the current is changing. So once it reaches the steady value, there won't be any deflection. As we have seen in the video, when the magnet is kept inside, there is no deflection. Though the magnetic field is there, no deflection. Exactly, primary and secondary. Okay. Now, when there is a change in the current in the primary coil, EMF is induced in the secondary coil, due to which an induced current flows through the galvanometer, which can be detected easily. And now, you disconnect the coil. Now, you take out the plug key. What will happen? Again, there will be some deflection in the coil, that is deflection in the galvanometer, but in the opposite direction. Do you know why? Because the current is flowing in the opposite direction. That is, from 0 to the maximum it is flowing in the first time. Now once you take that, the current will start reducing from maximum to 0. And this is also a change, isn't it? So when there is a change in the current, due to which the magnetic field associated with this coil will also change. And due to the change in the magnetic field associated with the coil, the EMF is also changed. EMF is induced, and due to which current is flowing. So this way, in both that way, whether it is increasing current or decreasing the current, there will be some deflection. But once you plug the key and keep it for some time, the deflection, after deflection, it will come to 0. That means when it is reaching the steady value or 0, when it is not plugged, in both the cases, the galvanometer will show no deflection or null deflection. That means when the current is not changing, when it is steady, no change in the current, no change in the magnetic field, no production of EMF, no production of induced current. This is what the experiment says. Okay. Now, as you have told already, the first coil is called the primary coil, the second one is called a secondary coil. Okay. Is that clear now? Right. Now, as we have seen that the change in the current in the first coil, the magnetic field or magnetic flux associated with the same coil will also change, and this is creating a change in the magnetic field around the secondary coil, because the same coil is placed in the same axis. So this will produce change in the magnetic field associated with that, and this is what creating a induced EMF. Now, to understand what is the direction of current, right, we are going to use the Fleming's right hand rule. Understand? In the left hand rule, what is the importance we have given? In the Fleming's left hand rule, importance is given for force. Exactly. Now the importance should be given for exactly induced current. Now, in the previous case, what we have taken as the first two, the direction of current and direction of magnetic field, and force is the third option. Now we are going to take the direction of magnetic field and the direction of force, then we will give the importance, finally the induced current. So this is how you have to write the rule. Look at that, the same sentence only. Stretch the thumb, forefinger and the middle finger of your right hand so that they are perpendicular to each other, this way, right hand. Right? Now, if the forefinger indicates, forefinger or first finger you can say, the forefinger indicates the direction of magnetic field and thumb indicates the direction of force or direction of motion of the conductor, then the middle finger shows the direction of induced current. Very simple one. So, you have to know the difference between the left hand rule and right hand rule. So by keeping both the hands, we can just differentiate it. Where we are giving importance for left hand rule, we are giving importance for thumb here. Here we are giving importance for middle finger here. So when you are giving importance for that, you keep that sentence as last, take the first two. Okay. So can you repeat that? Fleming's right hand rule now? Yes? Quickly. Yes. If condition. If that's all, exactly, very good, nice. So it's very easy to remember also. In the same way, you can write both left hand and right hand rule. And remember, the left hand rule is otherwise called there is other name for left hand rule, Fleming's left hand rule. Remember that. Exactly. What is the other name for this one? Fleming's right hand rule? Yes, because it is producing current, so it is called a generator rule. That's all. Okay. Now this is the electric generator, right? Similar to the previous one, similar to the electric motor, here we are going to see how the generator, what are the different parts of the generator, how is it functioning. Yeah. Yes, tell me. Exactly, that is what I was intended to say. Exactly. This is enough. The remaining part we can see tomorrow. You can proceed for your preparation. Thank you.